Dr. P here. For this video, we're going to go through an example of using work to find the distance a block travels after encountering a rough surface. So here we have a block of mass m. Its initial velocity is v1. It's already traveling. That block's going to travel down this frictionless ramp and then encounter this rough surface that has a coefficient of coefficient of kinetic friction of, let's just call it mu sub k. And the question is, how far does the block travel before coming to a stop? Okay, so coming to a stop, that means that our final velocity over here will be equal to 0 meters per second. All right, this is an energy conservation problem. I'm going to go ahead and start putting in some letters to denote different places that we could look at the energy. So we could look at the energy here at letter A, where the block only has kinetic energy. So if I wanted to say energy is conserved, the energy at A is going to be equal to the energy at B. The energy at B. There isn't anything that would take energy out of the system between A and B. But if we were to look what would happen when the block reached its final resting point, or point C, we could say, well, that energy will be equal to the amount of work that has been done by friction. So if we were to look at bar charts, at point A, this block is moving, so it has some kinetic energy at point A. Depending on where you put your zero height, we could put 0 here, meaning that at A, the block has no potential energy. But then once the block traveled down to point B, it would have a negative height, so it would have a negative potential energy, and I don't really like that. And so I'm going to put my 0 height at the ground here. And so the block at A will have some potential energy. At point B, we have all kinetic energy again. This block will be moving faster because it's traveled down the hill. And then work, remember, work is just the force that you have times the distance that the object has traveled. And so that force, the force doing work, if we were to draw a free body diagram on our block, the force that is doing work is going to be the force of friction. And the force of friction will be doing negative work. You're going to be taking energy out of the system. How much energy leaves the system, that amount of energy will be equal to the amount of energy that you had at the beginning. It's sort of weird to think about this. If it's something that you're having trouble with, just come see me and I'll help you figure out the way that works best for you, whether work appears on the left-hand side of the equation or the right-hand side. Okay, so this is the force of friction times the distance that it travels, which is what we need. Okay, so at this point, we can start plugging in our values, our variables. So 1/2 m velocity 1 squared plus mgh. Okay, perfect. All right, now for this problem, I don't really care what's happening at point B. It is not asking me what's the velocity when it reaches the bottom of the ramp. There's nothing weird that's happening here. This value is just equal to the sum of the kinetic and potential energy at point A. I don't really need to have point B concern me at all, so I'm just going to skip over that. Force of friction is mu sub k times the normal force times the distance traveled. Okay. The normal force, though, remember, is just, in this case, the normal force will be equal to the force of gravity, so mg. I have a mass in every term, so those can be canceled out. So I have 1/2 v1 squared plus gh equals, and if I divide both sides by mu sub k times g, that will give me the distance that the block will travel before stopping.